In this video, we're going to look at some important vocabulary words that we use when we're working with sequences. So to get started, we're going to let the pKs be a sequence as k goes from 1 to infinity. And it's important to first of all notice that this notation refers to the ordered list that looks like P1, P2, P3, P4, P5, P6, and so on. This is an infinite ordered list. Our first vocabulary word is going to make a way that we describe the P's themselves. The pKs are called the terms of the sequence. And the specific term, so the specific term pK is called the kth term of our sequence. So as an example, P4 would be the fourth term of the sequence. Now, there are times where we need to distinguish between the ordered list of numbers on the sequence and the image of the sequence. So I'm going to say there are times that we need to talk about the image of the sequence as a function. And so what I want to do is I want to remember that any sequence is implicitly a function that goes from the natural numbers to the real numbers, where P of k is just the kth term of the sequence. And if I want to look at the image of the sequence, I'm going to denote that as P of capital N, and this is a set. In other words, it is an unordered list that we typically have no duplicates. So without duplicates, because on a set we can get rid of the duplicates. But if we want to look at the sequence itself, the sequence itself is the whole list of, and it is an ordered list, so I want to get that word in there. This is the ordered list of all of the numbers that are represented. So this is an ordered list of typically an infinite number of terms. And I want to look at a specific example to make this idea very, very clear. So as an example, let's let pk be defined as 1 if k is odd, and -1 if k is even. Then my sequence of pKs looks like this. It starts off 1, -1, 1, -1, 1, -1, 1, -1, 1, -1. And this goes on forever. So it's an infinite list of 1, -1, 1, -1, 1, -1. But the image of this particular sequence is just the set containing 1 and negative 1, because all of the terms are one of these two numbers. And it's also worth pointing out that if I wanted to graph this particular list, graph this particular sequence on a number line, I would have the following picture. We would have P1, P2, P3, P4, P5, P6, P7, P8, P9, P10, and so on. So in other words, we can see that the image is actually just 2 points. But the sequence itself is hopping back and forth. It goes from here to here to here to here to here to here to here, and it just keeps bouncing back and forth between those two numbers. Now, there's one more concept. There's one more concept that I want to introduce right now, and that is the idea of a constant sequence. A constant sequence is simply a sequence. So it's a sequence that looks like pk, k goes from 1 to infinity, such that the image of this sequence is a singleton set. In other words, pk is equal to a for all k inside the natural numbers. So for all k inside n. And in other words, what this means is that this sequence is a very dull, boring sequence. It is A, and that list of A's goes on forever. Again, if I think in terms of graphing this, it's a very dull graph. Here is A, and I simply have that point for P1 and P2 and P3 and P4 and P5 and so on. So we never get away from that particular point. So there's some very basic vocabulary for dealing with sequences. Finally, I want to talk about what it means to have two sequences being equal to each other. So let's simply write this question down as when is pk, when is that sequence equal to this sequence? Well, we have to remember that sequences are functions, so I want to recall that this sequence here is a function going from the natural numbers to the real numbers given by p of k is equal to pk, and this sequence is a function going from the natural numbers to the real numbers given by q of k is equal to qk. And I know when two functions are equal, the function p is equal to the function q if and only if p of k is equal to q of k for all k's inside their domain, and their domain is the set of natural numbers, and that's going to be true if and only if pk is exactly equal to qk for all of the k's inside the set of natural numbers. So two sequences are equal when their terms, well, actually, let me say it this way, when they are equal term by term. In other words, pk equals qk for all k inside the natural numbers. I want to look at a specific example of what this means and what this does not mean. So as a note, if my pKs are defined as 1 if k is odd and -1 if k is even, and qk is defined as -1 if k is odd and +1 if k is even, then this sequence and this sequence, the sequence of p's and the sequence of q's, are not equal to each other, since p1 is equal to 1, and that's not equal to -1, which is q1. And it's important to note that this is true, that these two sequences are not equal, even though if I look at their image sets, the image of P is 1, -1, and the image of Q is also 1 and -1. And they actually look like they have very much the same graph. So if I look at the P's, let's see, here's here's -1, here's +1. The P's start out here, P1, and go here, P2. Then this is P3, and this is P4, and this is P5, and so on. But if I look at the Q's start out over here, Q1, and hop over here to Q2, and then Q3 is back over at -1, and Q4 is back over here. In other words, it's important to note that the pK list is 1, -1, 1, -1, 1, -1, whereas the Q list is -1, 1, -1, 1, -1, and so on. And these are not the same lists, so they're not the same sequence.